Okay, so we're going to bring in our voltage control voltage sources. And we're going to have 3 of these, so we'll just bring them all in. Okay, so now we got to move things around, create our circuit. And so let's open this up. Let's open that up here like that. Let's move this stuff around so we can create our little circuit here. We're going to use one of them here. I'm going to use one. Let's move this over. Move one here. Okay, so now we're almost there. Let's put the values as we did before. This is our, go ahead, this is going to be 10 milliohms. Okay, and this we're going to make RW. We'll just put a RW. Okay, and then this is going to be the L1 is fine, but we're going to make that 26 micro. Just like we had before. I forgot to connect those. And we need an injection point. So the injection point again is going to be a voltage source. So we'll come in and get our voltage source. And we'll rotate that. Okay. So a voltage source is going to go right here. Let's move this guy down a little. And then we'll attach it. Okay, and then we're going to make this a VAC. I'm going to increase 1 volt there, and that's your AC source. Okay, and basically we're going to inject this and call this label V of X and V of Y. So we'll just label that V of X. That's that point, and we'll make that VY. We could say that's VX hat, VY hat, and that would be VY. So our loop gain is going to be VY over VX. Okay. Now the values of here, remember that was 30K. Go back to your notes. This is 3.8K. And this is 1.3 nano. 1.3 nano. Okay. This is 2.2 nano. And this was 40K. Bottom resistor with the divider, that was 10K. Okay. And the reference voltage, we're using 1.25. And this V we'll just call V underscore ref. REF. Or just REF. Yeah. Okay. That's our reference. This is going to be our area amp. Like I said, our gain, we're going to make, that's your gain value where you add, double click that. I'm going to add minus 100,000. Let's move that a little up. So that's our gain of an op amp. We're treating that as an op amp. Later we're going to replace this with a real op amp. Now, since this is 1.25, and we know what our duty cycle is going to be roughly, it's going to be the 0.227 to create the input voltage of 22 volts. 22 times 0.227 is going to be 5. So we need an offset to push this up so that so when we put a real op amp in, it will be push up this output, which should be reflecting a quarter of this guy. So therefore the reference is 0.5. So we're going to make 0.5. We're going to push up the reference here so that this now will push this to be 0.5. Now the gain of this, that's going to be minus 11. Now where do we get that? That's the VG over the ramp height. VG is the input here, so we make that VG. No, VG. We make that 22. We have to make that one VG. So it will be VG, which is 22, over the ramp height, which was 2 volts, and that's 11. So that represents the modulated gain. Okay, this is just a gain of 1 now. Because where's our duty cycle? This one. That one we're going to put as 0.227. So in reality, this node here, we can label these now. That's V sub G. And that point right here with that label should be D, capital D times V sub G. Capital V and sub G. And that would be dV sub G. Then with a gain of 1, that's going to be the output voltage of 5 volts. That'll carry out DC. Now we got all the values picked out here. We need this value. That's our ESR, which is going to be 50 milliohms. The value is C is going to be 100 micro. And the load is going to be 0.5. So, you know, it's going to be, the characteristic impedance is going to be the square root of L and C. And we're going to have a 0.5 for the load. Okay, just like we have in the simulation. Okay, so it looks like, let's make sure we have this. We have all the values picked out. And let me see, why did we put a negative here? We could have just switched these two, put this into the reference and this to the minus, and then this would have been positive, because then you get a negative feedback. But this does the same thing. It switches these two. So we got a negative here, but we got a negative here. But it seems like a negative and negative. It looks like we have positive feedback. But that's not true, because we're going into here that's a negative. So we got 1, 2, 3 negatives. 3 negatives. Negative times negative is a positive, times negative is a negative. So we do have negative feedback, only because we're going into this negative port in here, which makes it negative. Okay, so we do have the proper feedback here. These are the proper components. And then we can run our loop gain. And if we get this over this, we should be able to get the transfer function. So we run this. And we want a AC analysis. Be 100. We're going to start this at 10 hertz to 1 megahertz. let's get rid of, let's go on this side, we get rid of this. We want Control C. Oh, I'm sorry. I have to right click it, divide, and then Control V. And there we go. There's our loop gain. So now what I just did is I ran, I need a Vy over Vx, okay? I need a Vy to Vx. So you just can't grab here to here, because then it's Vy minus Vx. I don't want a Vy minus Vx. I want a Vy over Vx. So I plot a Vy, I plot a Vx, and then I copy one and put a Vy over Vx, and that's the one we want. So I get rid of this there, and there's my phase gain. Hey, look at that. Exactly as we predicted before, as on our hand calculation. You could see that there's some queuing going on here. So if you look at 0 dB here, and we look at this this plot right here, we're looking at 0 dB. It crosses over at 10, 20, 30, about 35 kilohertz. But wait a minute, I thought we were supposed to cross over close to 30 kilohertz. That's what our analysis shows. We're supposed to cross at 30 kilohertz. Well, but you had a Q. If you get a Q, it moves the bandwidth out a little bit. See? And look at your phase margin, where it does cross over here. Your phase margin is here, and it's going to be right over here, which is your phase margin. You have to subtract the 90 degrees, and we have your phase margin is pretty high, because you can see we have the double poles, the ESR is 0 coming in. So now, and then your gain margin is where the phase does cross over at 0 degrees, but we never get there, so the gain margin is way out. It's greater than over 30 dB right here. So what we need to do is, let's get rid of this Q. And remember how you get rid of the Q is you decrew the circuit. So we come back into our circuit, just like we did before. We open this up, move this out a little. And then we're going to add in this, I'll just copy these two, kind of makes it fast. And then we're going to make this guy a damping resistance of, there's another 0, put a 0 there, 500, which is 0.5 ohms. And remember, this has to be about 5 times bigger, so we're going to make this 10 times. We're going to make this 1,000. It's 1,000 micro. So now I DQ'd it for sure. I don't have a problem. Now I'm going to put that in parallel with this. So you see at the frequency of interest now, it'll be this in parallel with the 0.5. So it then will lower my Q considerably. So let's run this and see if our Q drops down. Because you can still see a Q in here. You can still see the phase coming back in here and then coming back up. And there we go. Bingo. Wow, look at that. What do we predict? 30 kilohertz. What are we getting? 30 kilohertz. Look at our phase margin. Pretty high. 90 degrees phase margin. Pretty impressive. See? So this shows that, hey, we're getting our loop gain transfer function with this circuit. Now later, like I said, you could put in a real op amp in here, pop in a real op amp. Your reference is, of course, real. This is just a reference. And every other component is the exact components we have. And we're going to make this, we have our Vy, or we can call it Vout, and then Vout would be Vy. But we can see, we can label, we're going to get Vy, or really Vout, to Vg, input voltage. And we're going to get this closed loop and open loop. So let's look at what else we can do with the circuit. Okay, so now we have our nice loop gain. But now we want the output to input transfer function. And then we're going to inject a small signal current into here, and we're going to give it the output impedance over loop gain. And this is going to be output to input over loop gain because we have our loop gain here. So how do you wind up doing that? Well, we don't want this component anymore now because we want the output to input, so we can get rid of that. Let's go ahead and cut this out. And now we don't need Vx and Vy, we just call this V out now, and we just go ahead and attach this to this. Okay, so we're going to put a label here to be V out. Okay, boom. And now what we're going to do is we're going to say, okay, we're going to leave that's a DC bias here, but we're going to make this also, we're going to make this an AC source. So for the AC, it's 1. There it is. So we see we have an AC here. And now we have the closed loop gain. We have an AC here. And now we're not going to use this anymore, Vy over Vx. So we can just go ahead and get rid of that because there's no Vy over Vx. We took it out. And then we're going to go ahead and run this. And now we're going to look at the output here. What is that reference to? Well, this is the output to the input. That's what it is. When you press the output, it assumes you look at the AC signal. So we find the output to input. Look at that. You go ahead and match that with our hand calculation, and you're going to see it's pretty much dead on. So now we have our output to input transfer function over loop gain. Okay? Over loop gain. Now, in case we wanted to do an open loop output to input transfer function, that's not a problem. All we have to do is break this loop. Let's go ahead and break the loop. Okay, and this doesn't even have to be, it's going to be floating because it's open loop. And now let's go ahead and just tie this to this. There we go. Now this is open loop. Why? Because it never fed back. There's no feedback. You won't see this now. You won't see this 1 over 1 plus t. You're going to see something that's done like this. So let's go ahead and simulate it. Bingo! Look at that. That's your output transfer function. It's your open loop. What do we say? It's the open loop transfer function. Well, you could see at low frequency, what would it be? It'd be this in parallel with this stuff. Not this. These are open. At DC, low frequency, these are both open. So it'd be this in parallel with this. That's exactly what this is. Then you can see you have a low pass filter. You have the SR0. It's coming up. There it is. And you can see if we add 1 over 1 plus t, 1 over 1 plus t comes this way. Remember, we're at 30 kilohertz. We're at 30 kilohertz right in here. 10, 20, 30. That's why it opens this up to come up. And this is going down by a factor of 2. That's why you come up, you come down, and you have what you have for loop gain. So let's look at that closed loop again. We come back over here, and we put the circuit back. So we look at that again one more time. And we run it again. And there it is. It comes up and it comes down. Because what? Remember, the LC filter started coming down here at a -2 slope. This is a +1. This was a -2, so you get a -1. You get a +1 and a -1. When does this end? This ends all the way, because this is effectively looping until this is at 30 kilohertz. That's when this slope goes down more. And then you get the SR0, and that's why it's not going down at a bigger slope. Okay? So we have this 1 over 1 plus t. This is pretty cool. Okay, so now what we're going to do is we don't need this anymore, because now we're going to plot something different. We're going to inject a current source in here. Why? Because we want our output impedance. We're going to have our closed loop and then pull around and have our open loop. So we need to bring in a current source. That's a voltage source. We need to look for a current source here. There it is. There it is. Got my current source. Okay, let's go ahead and rotate that. We'll put our current source in here. Get rid of that. Hook that up. And remember, we want a small signal. We want AC. So we just put an AC current source here. Put a ground here. And we turn that guy into an advance. And we have a current source whose amplitude is 1. Bingo, AC 1. Now, we don't need an AC, so we need to get rid of that, because it'll confuse the computer of what's going on. We just want this, we don't want one injection here. We want the injection to be in here now. So now we have everything. We're going to inject it, and we're going to find the output now. What is that going to be? That's going to be the injected output impedance into this guy here. So we run this again. And look what we have. This here is what? Is really the output impedance. Why? Because this is an AC current of 1. So a voltage divided by 1 is the output impedance. That's why this represents the output impedance as well. Yeah, why? Because what does this do? It gives me this divided by this. Which is impedance, because that's the AC. So you could see, if you compare it again, you'll see that that's exactly what we get before. Now, we want to do an open loop. That's okay. How do we open the loop? We broke it here. Remember, the output impedance in open loop is not going to be divided by 1 plus T. So this should be a lot higher over here. Not here, because at high frequency is the same, because the loop gain's gone. When the loop gain's gone, the open loop output impedance is equal to the closed loop output impedance. Makes sense. Because you're plotting 1 over 1 plus T, and T ends off here. So let's go ahead and do our little clip. We cut that. And now what? We're measuring open loop. But let's attach this to here. And now when we go, there's no loop. There's no loop to modify this. So you're going to see us here. So let's run it. Let's see if I'm telling the truth. There it is. Minus 29 dB. It's coming up, and it comes back down in here. Let's look at the closed loop again. Let's make sure that this is lower than this. Let's go back in here again. This is our open loop output impedance now. Let's look at our closed loop. Just going back to that beginning again and run that again. Wow. We were up 30 something dB, minus 30. It pulled it down to what? Our loop gain. 1 over 1 plus T, which means T is much greater than 1, so it's pretty much 1 over T. So if this was if this loop gain bandwidth was, 60 dB, it would be 60 plus the 30, which is this. So this is what we have. This is pretty cool. We have just done everything, including open and closed loop transfer functions. Hopefully this will clear everything up. The next thing we're going to do is we're going to add on after we go through the circuits, we're going to actually put in a real circuit, time domain circuit, and then pulsate the current with this compensation values, and you should see we'll be tightly regulated. By the way, we can increase this resistor now. It shouldn't affect the Q that much because this Qs it. So let's make this 3. And we'll run this again. Remember, we're out here. So it should go up because the DC value went up. So let's run it again. And we see it's very much unaffected by the Q, because we did Q'd it here. Okay, well, thank you very much.